We're going to talk next about motion of objects in more than one dimension. Up till now, the kinematic relationships that we've developed for position and velocity and acceleration all have been quantities that we've graphed on a number line, but in more than one dimension we have to consider these as vectors. This means that each of them will have a magnitude as well as a direction. It's helpful to visualize what we mean by a position vector. In a three-dimensional coordinate system, having an x hat and a y hat and a z hat direction, in other words, x hat represents the unit vector in the along the x-axis, y hat the unit vector along the y-axis, and z hat for the z-axis. A position r is some quantity x times x hat plus y times y hat plus z times z hat. And up until now, these quantities could depend on time. So here might be our vector r, but just as we've been developing kinematic relationships between position, velocity, and acceleration for some quantity x as a function of time, it's possible that y and z all depend on time as well. In this case, if each of these functions is separately varying, and we go back to some of our experience with one-dimensional motion, then if this represents r at some time t1, if all these functions are separately changing, then the tip of the vector may move over here at some time t2. And may move over here at some time t3. And maybe over here at some time t4. And we could imagine drawing in this three-dimensional space a trajectory for what this position vector is doing. Over time. The tip of this vector would be sweeping out some complex shape where each of these components is given by these separate functions, x of t, y of t, and z of t. This is what we mean by a position vector in a three-dimensional coordinate system. Velocity is going to continue representing the change. So if r is a function that depends on time because x, y, and z do, v describes the change in r. So let's imagine just a simple two-dimensional coordinate system with x and y. There might be r1. Here might be r2. This quantity v is the change in r over the change in time, by which we mean r1 minus r2 over t1 minus t2. Since the two quantities in the numerator are vectors, and the two quantities in the denominator are scalars, then this is a overall vector. There's v as a vector. Actually, I've written this backwards. This is 2 minus 1, 2 minus 1. And where does delta r point? Delta r points from the tip of one vector to the tip of the other. Of course, if the change in time is very, very small, this has a sort of limiting sense of a derivative dr dt, by which we mean that the x component of velocity is dx dt, or the change in the x function. Vy is dy dt, and so on. That's, of course, in the limit where this time increment, delta t, is very small, but we can easily talk about the average velocity or the instantaneous velocity. Either way is okay. We just have to be careful what we mean, the differential sense or the averaged over some time increment kind of sense. So as an example, imagine that r of t, the position vector, is represented by the functions x of t is equal to 1 meter per second to the fourth times t to the fourth minus 3 meters per second t. And y of t is equal to 1 meters per second squared t squared plus 5 meters. So these things in parentheses here are just coefficients. And notice that the quantity for r will come out in meters. So I could ask us, please find this velocity function at different times and evaluate at t equals 2 seconds. To do so, I have to remember that the velocity as a function of time is going to be equal to some vx times x hat plus vy times y hat. And each of vx and vy will depend on time. So vx is going to equal dx dt, the time derivative of x, and that will equal 4t cubed minus 3. I'm ignoring the units, but remember what they are. Vy equals dy dt, and that equals 2t plus 0, because when I take a derivative of that constant 5, it is 0. At time 2 seconds, I plug in 2 here. 2 cubed is 8, and 8 times 4 is 32, minus 3 is 29. This has units of meters per second. And Vy, when I plug in 2 seconds, has the value of 4 meters per second. And V at 2 seconds is 29 meters per second x hat plus 4 meters per second y hat. And that would be the answer. Acceleration is the change in velocity over time, but now we have to describe this as a vector. And in the differential sense, again, this becomes dv dt. So A, the acceleration, has components, just like positions and velocities have components. Ax, the x component of this acceleration vector, will be the time derivative of the x component of velocity, or the second time derivative of x, where x is a function of time. A y will equal dv y dt, or the second derivative of time, of y. So these in general are functions of time as well, depending on how complex the functions x and y are. So in our previous example, we could try to evaluate what's the acceleration at time t equals 2 seconds. Well, let's remember that Vx was 4t cubed minus 3. And that means that Ax, which will be the time derivative of this, will be 12t squared minus 0. And Vy, we found, was 2t. And therefore, Ay had a value of 2. It's a constant. So the vector A at time 2 equals 2 seconds is 48 meters per second squared x hat plus 2 meters per second squared y hat. I'm having to think back now and make sure I have all my units right. But this coefficient out here had units of meters to the second divided by seconds to the fourth. I'm multiplying by a second squared, and so I have meters divided by second squared. And this coefficient came from my velocity. This was really in meters per second squared, and so it's retained that unit. So I temporarily dropped those, but I had to go back and reconstruct that. I make sure I have the right units for acceleration, because our problem is wrong. We dropped something and forgot our units.